Okay, hello. Welcome back. We're going to go over parametric equations part 2. The first 2 pages of this were due like a whole week and a half ago, and the rest of it was due on the Monday of Thanksgiving. Okay, we begin. The first problem, x equals 4 cosine t, y equals 3 sine squared t. This is actually kind of a repeat type problem. We did several problems almost exactly like this, so hopefully this is getting pretty easy. It's kind of like a warm-up to the packet. Well, without going through all the details, let's just say that because cosine is always between -1 and 1, 4 cosine is always between -4 and 4. So I'm just going to state that x is always between -4 and 4. I think we can do that in our head after having done it many times. What about sine squared? Well, since sine is always between -1 and 1, the square of a number between -1 and 1 will always be between 0 and 1. And when you stretch out this sine squared function, which is always between 0 and 1, when you stretch it out by 3, you get that y is always between 0 and 3. Okay, so hopefully I'm not skipping anything by just writing that like that. And of course, this function is periodic. Or this curve is periodic rather, because the x equation is periodic. In other words, the x coordinate repeats every 2 pi. The y coordinate repeats every pi. And in fact, I don't know, maybe this is just a good time to throw this out there, because I don't think I've done this before in this class this year. That maybe suppose someone wants you to make a very accurate graph of like y equals sine squared. What can you tell them? Well, in fact, sine squared is a sinusoid. And by that I mean, well, if you attempted to just make an intuitive graph of this using just kind of common sense, you would say, okay, well, sine of 0 is 0, sine of pi over 2 is 1, and when you square 1, you get 1. And then by the time you get back to pi, sine of 0 is 0 as well. But now, instead of going down at 3 pi over 2, instead of going down to -1, since we're squaring, it's going to make it positive again. So we get something that kind of looks like that. That's 2 pi, that's 3 pi over 2. And so you can see that the function is periodic. You can see that its period will be pi. You can see that it's always positive. But I can say even more than that, because there is an identity, and the identity is that, well, okay, it all comes from cosine 2t. What can I say about cosine 2t? It is, via the cosine of a sum formula, that's just cosine t plus t. So that's cosine t minus sine t. And so you get this kind of well-known and important trig identity for cosine 2t, and then this part we have reviewed in class. This can be rewritten in 2 different ways by substituting in for cosine 1 minus sine squared. Then I get 1 minus sine squared t minus another sine squared t. And so one of the formulas for cosine 2t is 1 minus 2 sine squared t. Okay, I'll put a box around this because I think this is one of the sort of, 7 or 8 trig identities that you really should know by heart or be at least extremely comfortable with because it comes up a lot, like right now, say. And, okay, great. Well, from this equation, I can just do a little bit of algebra 1 and solve for sine squared. So if I do that, well, I guess, okay. So I get 2 sine squared is 1 minus cosine 2t. And so I have really like now an entire formula, which is important in and of itself. It says sine squared is 1 minus cosine 2t over 2. This has a name. This is called a power reducing formula. And okay, I know this is all just review from Precalc B. But also, it's really important, and also, I'm not sure that Mr. Kirk necessarily stressed this heavily, this formula. But okay, there it is. Thinking about this another way, we see that one thing that this formula says is that sine squared is really just 1/2 minus 1/2 cosine 2t. In other words, it really is true that this function is just a cosine function with period pi smushed by a factor of 1/2, so amplitude 1/2, upside down and moved up 1/2. And so if we sort of move this thing up 1/2 and then see, okay, this is really just an upside down cosine curve. Okay, so I can say exactly what this sine squared t function looks like. And by the way, it's exactly this formula. This was sort of the stopping point on the way to deriving the half angle formulas. If you simply take the square root of both sides then and stick in for t, x over 2, then you get the half angle formulas. Okay, spending a lot of time on that for some kind of reason. That's because there's not much to this problem. I know my restrictions. There's no end behavior to talk about, so I guess I can just eliminate the parameter and graph it. How do I eliminate the parameter? Well, I kind of said, alright, oh no, I guess, actually this is sort of irrelevant to eliminating the parameter, because the simplest way of expressing sine in terms of cosine is with 1 minus. So I'm going to write this as y equals 3 sine squared t, and then I'll rewrite it as 3 instead of sine squared as 1 minus cosine squared, because that's the most convenient form to have it in. And so this is 3 times 1 minus, and what is cosine? It's x over 4. So this is x over 4 squared. Okay, so in a couple of short steps, I have now eliminated the parameter, and I can see that this is actually just a parabola. What's kind of a parabola? Well, it's going to be 3 times 1 minus x squared over 16. So one simple thing I could do is just write this as 3 minus 3/16 x squared. And if I do that, what do I get? I get this equation. And this shows that this is just a parabola. What kind of parabola? An upside down parabola. And when x is 0, y is 3. So down here, I'll maybe just graph this. 1, 2, 3, boom. And it's going to be, it's just going to be an upside down parabola. Is there anything more I can say about this? Yeah, I think so. I think it's worth it to write this in the kind of normal way that we write polynomials, which is with the leading coefficient, with the higher power first. And I can even factor out a negative 3/16. If I factor out a negative 3/16 here, I get x squared minus 16. Because negative 3/16 times negative 16 is positive 3. Okay, and the advantage of doing this is just that this is now seen to be x minus 4, x plus 4. Okay, so, one of those algebra things. It's nice to have our function represented in sort of multiple formats. And with these two formats I see, it's an upside down parabola, leading coefficient negative, so upside down, with roots at 4 and negative 4. So, like I was saying, there's really not much to this problem. It's going to look something like that. Now it's just a matter of adding in some t equals labels. Let's see when t is 0. Cosine 0 is 4. Sine 0 is 0, so we're going to be over here at 4, 0 at t equals 0. When I plug in pi over 2, cosine pi over 2 is 0, and sine is 1, so we're going to be up here at 0, 3 at t equals pi over 2. And okay, I guess I get this now, right? When t is pi, cosine pi is negative 1, so at t equals pi, I'll be over here at negative 4, 0, and then back again at 3 pi over 2, and back again here at 2 pi. And so this whole thing is just going, starting here, just going zhop, 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 forever. Okay, that was just kind of like a warm-up problem. Let's erase that and get to the next problem, which I think is kind of challenging. So okay, give me a second. Oh man. Okay. Great. Whew. Number two. Number two is similar. X equals 4 cosine t, y equals 5 sine t over 2. But now, one kind of subtlety that you might not have previously appreciated is coming up, which is that, okay, the period of cosine is 2 pi, which is to say every 2 pi the x-coordinate is going to repeat. But I do need to examine carefully 5 sine t over 2. Now what do I know about 5 sine t over 2? Well, it's like sine but stretched out by a factor of 2. And in fact, the period of this is going to be 4 pi. And the period of this is going to be 2 pi. So the x-coordinate repeats every 2 pi. Knowing in advance that the y-coordinate repeats every 4 pi, I better, if I'm going to be point plotting this, I better consider t-values on the entire interval, 0 to 4 pi. I don't have to start at 0, but I might as well. So I'm going to sort of, this is something that's come up kind of once or twice, which is that if you have some equations which are periodic, then you need to examine what their periods are. And if the x-coordinate is repeating every 2 pi and the y-coordinate is repeating every 4 pi, then this entire curve is going to repeat every 4 pi. And so I'm going to sort of decide in advance that I intend to graph this curve on the interval from 0 to 4 pi. And then I'll just say, okay, and so on and so on. Okay, now I have to, and then again I get some things which I think are obvious by now. I don't know if I want to go through the details, but x has a, x is 4 cosine, so the amplitude is 4. So the x-coordinate is always going to be between -4 and 4, and the y-coordinate is always going to be between -5 and 5. Okay, great. It's periodic, as we already mentioned, so I think the only thing left to do is just eliminate the parameter and then graph it. Well, when I go to eliminate the parameter, I need to make some decisions, and I bet some of you kind of just reached for the half-angle formula, and that's fine. You do get some kind of square roots and things get a little bit ugly and stuff like that. I hope I did a good job just a minute ago in sort of convincing you that the half-angle formula is really just kind of really just the double angle formula, but sort of written differently. And by that I mean, okay, what do I mean by that? What I mean by that is, sure I have a half-angle formula here, but I could just as well think of t over 2 as my variable, and then t is like twice that. So the smoothest way to do this problem, and maybe this does require a little bit of sort of foresight or a sort of appreciation of the half-angle formula. Well, okay, what do I mean by that? What I mean by that is, how do you get the formula? How do you get the formula for sine t over 2, let's say? I already did this 10 minutes ago, but I'll now do it again, sort of like, really fast or something. Well, you get that cosine 2t is, as we said, 1 minus 2 sine squared t, and that's the derivation we already did. And therefore, let's see, am I doing this right? No, it's the other one that I wanted. It's the, sorry, what am I doing? Yeah, that was right. 1 minus 2 sine squared t, yeah. And then, therefore, sine squared t is 1 minus cosine 2t over 2. And then sort of like the next thing to do, I mentioned it, but I didn't actually do it, is to just stick in for t, t over 2. So you get sine squared t over 2 is 1 minus, but now when you plug in t over 2, you get 1 minus cosine t over 2. In other words, and then if you take the square root of both sides, you get the half-angle formula. In other words, the half-angle formula just is really the double angle formula, kind of in disguise. Okay, therefore, let me just look at this 4 cosine t. The way to do this smoothly without getting into discussing square roots and stuff like that is to basically just do that, right? Take 4 cosine t and rewrite it as sort of 2 times t over 2. I mean, there are a lot of sort of equivalent ways of doing this, but to me this is the smoothest way. And then apply the double angle formula. So what is 4 cosine sort of 2 theta? Well, it's 1 minus sine squared t over 2. And ultimately, I guess what I'm doing here is just this, right? I'm really thinking of the double angle formula for cosine sort of as my thing here, and so I'm just applying it like that. Whew, very windy. Okay, so hopefully that's clear. Where my sort of variable now is t over 2. Okay, there are also just many other equivalent ways of getting the same thing, but you do end up with now 4 times 1 minus, well, what is sine t over 2? It's y over 5. So this becomes y over 5 squared. And now we're just on our way to having a nice equation here. What is this? It's 4 times 1 minus, hope I'm doing that right. Yeah, sure I am. Sine t over 2 is y over 5, so that's y squared over 25. And so this is 4 minus 4/25 y squared. And okay, because this is getting kind of maybe repetitive, let's just graph it and sort of move on. What can I say about this? Well, it's going to be a sideways parabola. And from the outset, I already saw that the whole thing was going to live between -5 and 5. 1, 2, 3, 4, 5. 1, 2, 3, 4. And between -4. Oh, oops, I got that backwards. So let's try that again. Between -5 and 5 along the y-axis, and between -4 and 4 along the x-axis. So we got like this kind of situation. And okay, what is it again? It's a sideways parabola because it's an x equals y squared parabola, but also the leading coefficient is negative, which means it's going to open left, not right. And well, you can just see, right? Plug in 0 for y, you get that x is 4. So boom. And what else? Plug in, well, let's find out where I am at the top. I think I know already. When y is 5 or -5, x is 0. Sorry, did I do that right? X is 0. 1 second. When y is 5 or -5, then that cancels and x is 0. That's kind of not what I was expecting to happen. Have I made some kind of mistake? 4, 1 minus sine squared. Oh my gosh, I made a horrible mistake. Oh, terribly embarrassing mistake that you're maybe kind of screaming about. Of course, I just used the wrong formula. I had it even written right here on my board. Oh man. Bad video. Never mind. We move on. This is 1 minus 2y squared. Okay. So this is 8/25. Okay, I just failed to use the correct trig identity there. Even though I had it written right on my board, I just kind of spaced it out. Anyway, I did catch my error because there's sort of a redundant method that we have here. But okay, now doing this properly, when I plug in 5 or -5, that cancels the denominator. I get 4 minus 8 is -4. Sorry about that. Anyway, here we are, and now this is kind of what I was expecting to happen, which is a sideways parabola opening left, as I said. Okay, and great. What is this point? 4, 0. What is this point? -5, -4. Oh man, -4, 5 is what it is. And here we have -4, -5. And the maybe only interesting part of this problem, it's kind of an ugly parabola, something like that. Okay, the only interesting part of this problem is what happens, or sort of how does it get traced out? And the answer is it takes a while, right? It takes, it's going to take a whole 2 pi, 4 pi to do it. Okay, so let's plug in some points and kind of just see what happens. Well, if you plug in 0, you're going to be right here, and maybe now I could plug in pi over 2. Well, something kind of interesting happens if I plug in pi over 2. What do I get? Here, cosine pi over 2 is 0, so x is 0. Now, when I plug in pi over 2 here, I get sine pi over 4. Sine pi over 4 is root 2 over 2, or perhaps it's best to think of it as 1 over root 2. So what is 5 divided by root 2? Like about 3.5-ish? So actually, I'm going to have this point over here, which is 0, 5 over root 2. I guess if you multiply 1.4 times 3, you get 4.2, so it's really, yeah, it really is like 3.5. And that's happening at t equals pi over 4. No, t equals pi over 2. But when you then plug in pi, cosine pi is -1, so I get -4, and sine of pi over 2 is 1. So that's how I'm up here at t equals pi. And, okay, I just promise you, if you plug in 3 pi over 2, sine is still that same positive number, cosine is 0, so we're back again at 3 pi over 2 here, and when t is 2 pi, cosine 2 pi is 1, and sine of pi is 0, so we're back again at 2 pi. So notice that if I only went from 0 to 2 pi, I would sort of only get the top half of this parabola, but I think the entire thing is being traced out, and therefore I'm going to have to just, continue. Like, what if I plug in 2.5 pi, 5 pi over 2? Well, now, if I plug in 5 pi over 2, cosine of that is 0, but 5 pi over 2 over 2 is 5 pi over 4, sine of 5 pi over 4 is negative root 2 over 2. And so I get this point over here, which happens at t equals 5 pi over 2. What is that? It's 0, -5 over root 2. Okay, and finally, if I go all the way to 3 pi, cosine 3 pi is -1, so that's -4, but sine 3 pi over 2 is -1. So that's how I get to this point when t equals 3 pi, and then 7 pi over 2 is going to bring me back here, and then back at 4 pi I'm going to be back at this point again. So it's just like the x-coordinate is repeating every 2 pi, so jump, 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 jump. That's what the x-coordinate is doing, but the y-coordinate is repeating every 4 pi, so it's kind of just like pi, 2 pi, 3 pi, 4 pi. That's sort of the deep way of thinking about this, right? Is that if you have a point moving sinusoidally, well, okay, I'll leave it at that. All right, this is going way too slow. Let's push on to problems that are legitimately new. This was new only in the fact that you had to be kind of careful with your trig identities and with your the period of the functions. But okay, this next problem is kind of easy and cute or something. I don't know. X equals root t. This is number 3. Y equals -3 root 16 minus t. Okay, so we can just do our basic stuff with this. Let's see, what's one thing? Well, I can only take the square root of a positive number. So it seems that t must be greater than 0. But it also seems true that x must be greater than 0, because the output of the square root function is always positive. Next, well here, this is going to crash if t is too big. Specifically, if t is like 17 or something, that's going to crash. So therefore, if 16 minus t has to be positive, then this is telling me that t has to be less than 16. In fact, t can be 16. If you plug in 16, then you just get 0, so that's okay. And up here as well, I think t can be 0, so t is greater than or equal to 0. But the output of the square root of 16 minus t will always be positive, and so if you're multiplying that by -3, I think y is always going to be negative. Similarly here, x could be 0 when t is 0. Okay, that was a little bit rambly. What have we just learned from all of this put together? Well, I just learned that, in fact, this curve only allows t-values between 0 and 16. Okay, therefore, there's sort of no end behavior to talk about here, and I think I can just get straight to eliminating the parameter. How can I eliminate the parameter? Probably the simplest thing to do, I suppose, is just do it. Okay, so take x equals root t, square both sides, so you get the t equals x squared, and maybe just stick that right in, so you get y equals negative 3 times the square root of 16 minus x squared. Alright, so now it's sort of depends on you to recognize this. Do you recognize y equals negative 3 root 16 minus x squared as kind of like a known function? Well, you should, because y equals root 16 minus x squared is the kind of function that we learned about in Precalc C. It's sort of a basic one that you should know and recognize. What is it? It's a semicircle, and that can be seen by squaring both sides of this relationship, and we get that y squared is 16 minus x squared. In other words, x squared plus y squared equals 16. So another way to think about it is if you just take the circle centered at the origin with radius 4, and you sort of just solve for y, then you get this. And so it's not quite the entire circle of radius 4, this is just a review, but it's the top half of that semicircle because y is positive. By taking the square root, we only consider the positive y values. Okay, so that's just the semicircle function. That's just kind of a basic function that you should know, in my opinion. Therefore, what is this function? Well, it's just that, but stretched out by a factor of 3 and flipped upside down. Okay, so what is this thing? Well, it's just the semicircle radius 4 function, but stretched out by a factor of 3 and also upside down. So boom, 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 boom. But also, x has to be positive and y has to be negative. So let's see, am I doing this right? Or did I make some kind of horrible mistake again? No, I think we're good. Why did I think... Oh man, having some rough times with mistakes and stuff. Isn't that just 4, 3? I think it is, right? When you plug in 0 for t, then you're just going to get negative 12. Why is that? Oh, of course, because it's the, oh man. So yeah, it's the, without the 3, it's going to be, without the negative 3, it's going to be root 16 minus t. Yeah. Without the, look, I guess looking here, without the, when it comes to just making an accurate graph of this, which shouldn't be hard, but I was about to mess it up, that when you plug in, yeah, well, maybe there's nothing to say, let's just do it. It's the semicircle of radius 4, but then it's been stretched out by a factor of negative 3. So we're all the way down here at negative 12. And here is 4. Okay, so what do we get? We get kind of like a stretched out quarter circle. That's really what this is. It's a semicircle, but it's the bottom half of the semicircle, but actually it's only a quarter of the circle, and this circle has radius 4, but it's been stretched out by 3 in the y direction. So that's just all there is to this problem. This is 4, 0, and this is 0, negative 12, and kind of there it is. So let's just add in some t equals labels and then we'll be done. Well, when t is 0, where am I? I'm at 0, comma, negative 12. So here I am at t equals 0. And then, well, what happens? As t gets bigger and bigger, x gets bigger and bigger. And so, okay, I don't think there's really anything left to do, right? Let's just go for the end. when t is 16, I get 4, comma, 0. And so here we are at t equals 16. And so the arrows just kind of look like that, and that's all there is to it. Okay, let's pause this video for a minute. Okay, continuing, here's number 4. This is a very exciting problem, actually. X equals cotan t, y equals 2 sine squared t. What's up with this pair of parametric equations? What path what path is traced out by them? Okay, well, this is a great opportunity for us to review many different things. And okay, maybe just straight off, let's take a look at these two equations. What can I say about cotan? Well, it's important that to do this problem that you understand cotan very well. Maybe you're the kind of person that can just, in an instant, produce an accurate graph of cotan. I can. Okay, and sine squared we already talked about kind of extensively in the earlier part of this video. Now, and we discussed, by the way, that the period of 2 sine squared t is in fact pi, and that because it's really just a sinusoid, well, cotan also has a period of pi. So what pi length interval should we sketch this curve? Well, I guess cotan has a kind of nice representation on the interval 0 pi. So making kind of a graph over here of x versus t, I think this is a good thing to do. Maybe a little smaller though is fun. So boom, here we go. This is the t-axis, let's say, and this is the x-axis. Well, cotan kind of looks like this. So if you want to sort of think of it in terms of the unit circle, cotan is x over y, and zone out for a second. Cotan is x over y. So if cotan t is x over y, then what does that say? Well, if you pick a point which is very, very close to 0 on the unit circle, then the x-coordinate is nearly 1, but the y-coordinate is very, very tiny. And so this is 1 over very, very tiny, which means that the cotan will be like positive infinity. And so we get something that kind of looks like that. Then by the time you get to pi over 2, by the time you get to pi over 2, x is 0. And now, once you're in the second quadrant, cotan will be negative because the x-coordinate will be negative and the y-coordinate will be positive. And by the time you get back over here to almost pi, then you have a similar situation. Cotan is x over y. Well, the x-coordinate is pretty much -1 almost, but the y-coordinate is a tiny positive. So -1 over a tiny positive is a huge negative. Okay, this is just me simply, for whatever reason, re-explaining the entire graph of cotan as if you have never seen it before. So at a very sort of quick pace, that is why cotan looks like this. And I do think this is one of the functions that you should simply know. You graph this in Precalc C. And all right, having looked at it, it seems, and then this is going to just keep repeating every pi because the period of cotan is pi. Well, then I think what I'm going to do then is look at this curve on the interval from 0 to pi. Of course, I can't take the cotan of 0 and I can't take the cotan of pi, but I can take the sine of anything. So this is the particular pi length interval that I will sketch this curve on. Okay, having established that and having this nice curve, maybe I just go straight to the, and I guess we should say some things about y. Y has to be between 0 and 2. Okay, let's look at some end behavior. Now, of course, there's no end behavior because the function is periodic, but there are values near which cotan becomes huge. So I really should in fact must, note the behavior of x and y near these important points, like when t is a tiny positive and when t is a tiny bit less than pi. So, okay, hopefully you thought to do that as well. And, alright, let's go. Well, maybe this is just kind of not so hard because my picture already is telling me that cotan is like infinite, a little bit more than 0. What about y? Okay, well, sine of 0 is basically 0, but if t is a little bit more than 0, then sine squared would be a little bit more than 0. So, okay, this is just 0 plus, I guess. Have I done that wrong or something? No, I guess that's okay. Not what I was expecting. Okay, how about over here? If t is a little bit less than pi, well, sine of pi is 0. So if t is a little bit less than pi, then this is going to be almost 0 as well. And since it's squared, it will be positive. So again, y is going to be 0 plus. But just to the left of tan, cotan is going to be negative infinity. So okay. Good. What's left? Just eliminate the parameter and sketch the curve. Okay, let's eliminate the parameter. Now, this is kind of an interesting one. I have no idea really what to do now. I have to do definitely some trigonometry. So, I don't know. There are lots of kind of ideas, some of which are better than others, but I think no matter what you do, whether it's efficient or not, it's going to work out eventually as long as you don't give up. So, for example, you might start with x equals cotan. I can't even remember the sort of cool, smooth way to do this, so I'll just do whatever the first thing I think of. Cotan is cosine t over sine t. That's one option. And, okay, so perhaps maybe we just square it. Why? Because y is essentially sine squared. So I kind of want that to be squared or something like that. So maybe you think that that's unreasonable to think of that. But anyway, if you square, then you get cosine squared over sine squared. And now I think I know what to do because I want to express everything in terms of sine squared. So really I want to write this as 1 minus sine squared over sine squared. And each of those can be rewritten as y over 2. And so I get x squared equals 1 minus, this sine squared is y over 2, so I just get y over 2 over y over 2. Yeah, I think this is one of the nicest ways to do this. And if you keep simplifying, then by, say, multiplying by 2 over 2, then you get 2 minus y over y. Well, that might strike you as not immediately very nice, because what is x squared equals 2 minus y over y? What am I supposed to do with that? Well, just keep on going and don't stop. So maybe multiply both sides by y, and we get x squared y equals 2 minus y. Well, I have a y equals bias, so I think I'm just going to solve for y. And if I do that, I get x squared y plus y equals 2. Now I see what to do. This is going to be y, x squared plus 1 equals 2. And so my final answer is y equals 2 over x squared plus 1. And see how I kept kind of manipulating, doing algebra, not just stopping when I eliminated the parameter, but continuing to kind of massage that relationship between x and y until it looked like something which was recognizable. And I think this is the kind of thing I know how to graph. By the way, it's slowly coming back to me that there was a cooler way to do this because, let's see if I remember. The super smooth thing to do would be to write this as, okay, ready? Watch this. It is a fact that I think this is the thing to do, is the fact that cotan squared t plus 1 equals cosecant squared t. This is one of the trigonometric Pythagorean identities. So I'm now sketching this. I did this kind of the long way. Now I'll explain the sort of smooth way, if you're super cool, that you could have figured out this relationship with much less work. Okay, well, what's cotan squared? It's, of course, it's just x squared. So I get x squared plus 1 equals. And what's cosecant squared? Well, cosecant squared is 1 over sine squared. So this is like 2 over y. Boom. That's pretty exciting. Now reciprocate both sides of this, and you get y over 2 equals 1 over x squared plus 1, and then you send it right here. Okay, so you just have to use all the various relationships between sine, cosine, cotan. Here I use the Pythagorean identity for cotan and cosecant, but if you weren't that creative, then you would have to do what I did initially, which is to use the Pythagorean identity for sine and cosine. That's ultimately what I did here, right? I used the fact that sine squared plus cosine squared equals 1. Okay, a lot of exciting things happening. So now what is this, of course? So this, your ability to find this thing in the box helpful depends on your comfort in graphing 2 over x squared plus 1. Well, that's a rational function, so I think it's the kind of thing that we should have some experience graphing. I think normally I assign this problem, but I think this year I didn't. So maybe you've never seen this before, but it's really not hard to imagine what it looks like because, well, I think the thing to do if you're just a kind of a smart pre-calculus A student or something like that is, consider y equals x squared. We all know what that looks like. So what does y equals x squared? Well, maybe I want to go straight for x squared plus 1. I take it back. What does x squared plus 1 look like? Well, it looks like x squared but moved up 1. And now, what happens when you reciprocate that? Well, just kind of performing a graphical reciprocation of sort of arbitrary functions is a thing that you practice in Precalc A. And the answer is when you take the reciprocal of something that's positive, the reciprocal of big things become little, and the reciprocal of little things become big. So this function is 1 or more, therefore the reciprocal will be 1 or less. And what you're going to get is something, 1 over a huge thing is a small thing, and as this function gets smaller, the reciprocal gets bigger, and the biggest it ever gets is 1. And so this whole curve, y equals 1 over x squared plus 1, just looks like a little boop. And of course, then when you multiply by 2, it just gets a little bit bigger, so 1, 2. So, like that. Okay, all of this was preparatory work. Remembering the graph of cotan, graphing cotan, using it to answer these questions, doing a bunch of algebra which involved trig identities, thinking about how to reciprocate a parabola to get the accurate graph of this rational function. And now, finally, we just do the problem. So, let's make now kind of an accurate graph here. So here's 1, here's 2, boom, boom. And actually, you can see that when you plug 1 in here for x, then you just get 1. So that's a nice point. And of course, this function's even, so I get something like that. And basically, okay, and this shape has a name, in fact. This is called the Witch of Maria Agnesi. Whoa. What's up with that? I keep forgetting to look up the details of this, or rather, I look up the details of it and then I keep forgetting it each year. But it's something like, so who is Maria Agnesi? She is a mathematician, a famous, kind of famous Italian mathematician from, I don't even know, maybe 200-300 years ago. And she investigated this curve. This 1 over x squared plus 1 curve, and this is kind of important enough that it's going to come up later in calculus for sure. Why is it called the Witch of Maria Agnesi, besides the fact that people just like exciting names for things? I believe the story is that due to some kind of translation error or something like that. I think she she used the word adversary or adverse or something like that. She used to describe this curve. But in Italian, adverse has like a double meaning as like, the devil or something like that. And so it got kind of mistranslated as some kind of devil curve. Okay. Woo. Finishing it off, of course, I bring back in the fact that this curve is sketched out parametrically. So how does it get sketched out parametrically? Well, let's begin. Where am I at t equals 0 plus? Answer at infinity, comma 0 plus. So that's kind of nice. Here I am at t equals 0 plus, and looking at this kind of more carefully, I see, well, what's happening? My x-coordinate starts off infinite, and between 0 and pi over 2, it goes back to 0, and then between pi over 2 and pi, it goes to negative infinity. So you should see yourself sketching out this curve sort of from right to left. The x-coordinate goes from infinity to negative infinity. And so I must be here at t equals pi over 2, and sure enough, when you plug in pi over 2, cotangent pi over 2 is 0, and sine of pi over 2 is 1, so you get 1 squared is 1, and you get 2. Whew. So here is this point 0 comma 2, as we already knew, and you could just plug in another value like pi over 4. Cotangent pi over 4 is 1, and sine of pi over 4 is 1 over root 2, so when you square you get a half, and indeed this point 1 comma 1 happens at t equals pi over 4. And okay, let's just finish it off. When I plug in 3 pi over 4, cotan 3 pi over 4, is negative 1, and sine of 3 pi over 4 is the same as sine of pi over 4. So we get this other point, negative 1 comma 1. That's happening at t equals 3 pi over 4. And finally, as t approaches pi over 2 minus x goes to negative infinity and y goes to 0 plus, and so we get this t equals pi minus behavior. And so it all makes sense. This was, I thought, a kind of a hard problem and sort of a fun one that was due last week that we didn't go over. I think there's one more thing left to say, which is that what we have just sketched accurately explains what this curve does on the interval from 0 to pi, but of course it doesn't just do this once. It does this over and over and over again. So because this function is periodic with period pi, as soon as we get here, what actually happens is a teleportation. And we teleport back over here. And so there's some kind of cha-cha. And so this thing, how this thing actually works is that we start here at some kind of 0, or every k pi basically begins out over here. It takes us pi to go, and then we teleport back and we sort of do it all over again. All right, that was number 4. I don't think it gets that exciting again. Okay, let's erase it and just keep going. I see that this video is taking forever. Apologize for the problems 1 through 3. I think I was just a little bit off and kind of tired and going a little slow Monday morning, and even made a big mistake at one point, but now I am pumped. Let's do 5, 6, and 7, all of which are kind of review and not that exciting. So let's do them quickly. What is 5? X equals e to the negative t plus 3, y equals t. So this is kind of barely parametric at all, because really y just kind of is t. And well, all right, let's go. What can I say about t? Well, I can take e to the anything. So I think there are no restrictions on t. Are there any restrictions on x? Well, e to the anything will be positive. So x will certainly be greater than 0. And I think that's all I have to say. What else? Well, I think nothing else. Let's see what happens as t approaches infinity, and as t approaches negative infinity. Well, okay. Let's just just kind of complete this little chart, and then we do it. Well, as t goes to infinity, that's pretty much e to the negative infinity. So e to the negative infinity is going to be a tiny positive. Well, y will just go to infinity. And if you plug in e to the negative infinity, that's going to be huge, and y is going to negative infinity. So, all right, hopefully eliminating the parameter will help me. And okay, here's where, I mean, it gets a little controversial, right? What you want to do is you want to just say, look, what's the absolutely fastest way to eliminate the parameter? Well, it's just, y is just t, so I sort of stick y in for t and I'm kind of done, you know, in 0 lines or something like that. So here's where we have to have this conversation. Yeah, technically you did eliminate the parameter. There are no t's left, so that's good. But the whole point of eliminating the parameter is to find the relationship between x and y. And this is a relationship between x and y, but, okay, unless you are very, very comfortable with x equals equations, if you've completely eliminated your y equals bias, perhaps you can know what this graph looks like, but for normal people, this is sort of hard, right? This is the e to the negative y, wait, x equals e to the negative y, what is that? So I think the better thing to do here would be to solve for y. Let's do that. How do I do that? I take the natural log of both sides. So here, this is ln x, and here, of course, the ln of e to the negative y plus 3. Well, it's just the very definition of natural log, that the natural log of e to the something is just that thing. And so we get ln x equals negative y plus 3. Ah, okay. So what's up with this? Actually, this was very similar to the quiz problem we had. So what we end up is y equals 3 minus ln x. And that to me, for a sort of normal person, that's much more satisfying. I know what the graph of 3 minus ln x looks like, and so this will just be kind of easy for me. What does it look like? Well, regular natural log looks like that. So upside down natural log is going to be, you know, flipped upside down. And then the whole thing is going to get moved up 3. So whereas this kind of, I call it the magic point, would normally be here at 1, 0, it will still be here at 1, 0 in the negative ln x curve, but then it's going to get moved up 3. So I think we can safely squeeze this in here. What's going on? Well, I have this point 1, comma 3. And there it is. Furthermore, there is going to be some kind of vertical asymptote. And what we're going to see is a curve that looks basically like this. And in fact, this is going off, and this will go to negative infinity, but very, very slowly. All right, let's label this thing. Where do I begin? I begin at time negative infinity, out at infinity, comma, negative infinity. So this is t equals negative infinity. So therefore, I'm tracing the curve this way. Seemingly. So boom, 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 boom. And now what happens as t approaches infinity, then I am up here at 0 plus, comma, infinity. So that's up here, cha-cha. And let's see, what's another good number to plug in here? I don't really like 0. I think 3 is a nice number to plug in, because if I plug in 3, I get e to the negative 3 plus 3. Well, that's e to the 0, so that's 1. So this point 1, comma 3, in fact, happens when t equals 3. And of course, you could get other points. Say if you plug in 2, say, then you'll get e to the 1, comma e. So yeah. So therefore, there is another point, e comma, 2 comma, no, I got that wrong, e comma 2. Yeah, so actually this is looking kind of right, because if that's 1 and that's 2 and that's 3, then e comma 2, I think I did that exactly correctly. That happens when t is 2, I think is what I said, right? Let me just double check on that, e comma 2, yep. Whew, okay. I think that's all that deserved, maybe plus more. More. Number 6. X, this is very much like the quiz problems actually. X equals negative e to the t, y equals e to the negative 2t. Okay, and here is maybe one of those times where it's worth it to just do some quick preparatory graphs. So negative e to the t, well, I just know e to the t, I know what it looks like, so it looks like that. So negative e to the t is going to look like that. So this is just a nice, tiny, little helpful graph of x versus t, and perhaps a tiny little graph of e to the negative 2t, which is going to look like a standard decaying exponential. So it's going to go kind of like this, cha. So that's y versus t. Okay, and taking the time to make these little graphs, or if you don't want to draw them, you should at least think them, helps me answer the question. Of course, there are no restrictions on t because it can be anything, but x has to be less than or equal to 0, and less than 0, and y has to be greater than 0. Those are the two facts I can get either by examining the formulas or by looking at these graphs I just made. It's kind of the same thing. Right, we keep going. Having done restrictions, let's look at end behavior. And, well, okay, so as t goes to infinity, as t goes to infinity, as t goes to negative infinity, I shall look at individually what happens with x and y. So, oh yeah, doing the math, cha-cha-cha. Well, as t goes to infinity, in x is going to infinity, y is going to 0 plus. I just look at my graphs. And as t goes to negative infinity, x is going to 0 minus, and y is going to infinity. Perhaps it's better to kind of talk them out. Well, you can reason these out just by going directly from the formula, but I think you sort of see how helpful it is to make a little sketch first. It makes answering these questions kind of easy. All right, finally we eliminate the parameter and graph the curve. How should we eliminate the parameter? I don't know, but I do know I have a y equals bias. So let me write y equals e to the negative 2t in a slightly different form. So here I'm using exponent rules. Well, yeah, what is e to the negative 2t? It's kind of just like 1 over e to the 2t, right? Yeah, that is what it is. That's just what negative exponents mean. And you need to be smooth enough with your exponent rules, algebra, etc., experience, whatever, to see 1 over e to the 2t as 1 over e to the t quantity squared. Of course, by exponent rules, that's just true, that e to the t, to the 2 is e to the 2t. And that's really nice because e to the t is just negative x. So that's how we get to 1 over negative x quantity squared. And of course the negative is gone, and so this is just y equals 1 over x squared. Okay, so one way or another, you have to eliminate the parameter, and we have just determined that the relationship between x and y is y equals 1 over x squared. I know this curve. It is the volcano. It's the reciprocal of y equals x squared, but seemingly only the left half of the volcano is being sketched out. And so, all of my experience graphing 1 over x squared, I'm not going to go through the logic again of why it looks that way. You just take, sorry, it looks very asymmetric. You just take the, or I guess it should, no, but it should look asymmetric in the other way. Anyway, never mind that. But all of my, yeah, I've just done this kind of problem before, right? Taking the parabola y equals x squared and performing a reciprocation. All right, let's just finish it off. Where are we at time negative infinity? Answer at 0 minus comma infinity. So exactly as this curve predicts, we are going to be up here at t equals negative infinity. I guess this is a good problem, and maybe not that easy actually. What's a good number to plug in? How about 0? If you plug in 0 for t, e to the 0 is 1, so you get negative 1, but here you get e to the 0 is 1. So this point, negative 1, 1, is indeed happening at t equals 0. And I guess that as t approaches negative infinity, I'm going to be approaching... did I flip that? I think I must have made a mistake here. I was being kind of careless. As t approaches negative infinity, x goes... Sorry, something went awry. Something went wrong. Let me just double check everything. As t goes to infinity, x goes to... That's just wrong. As t goes to infinity, x goes to negative infinity, and as t goes to infinity, y goes to 0 plus. As t goes to negative infinity, x goes to 0 minus. That's just a fact. And y goes to infinity. Okay, so I don't even know what I had up there before, but that was just sort of all wrong. Now let's double check again. Where am I? Yeah, okay. So yeah, at time negative infinity, I'm at 0 minus comma infinity. And as t approaches infinity, I end up at negative infinity comma 0 plus. Okay, so once again, I made a mistake. I lost track even of what mistake I made, but anyway, I caught myself, so that's what's happening. Okay, good. Sort of 2 more easy ones or something, and then a hard one. This parametric number 2 packet's pretty hard. This will be our last real thing with parametric equations. Okay, but then this comes up a lot in calculus, or, well, comes up somewhat in calculus. Okay, so, number 7. Whew. Yeah. Here we go. X equals negative 3 cosine t, y equals 5 sine t, and let's do number 8 as well. X equals t minus 3, t minus 5, y equals t. Put that over there. Okay, I think we can do both of these pretty easily. This one I've seen before, right? Well, cosine is always between negative 1 and 1, so negative 3 cosine will be between negative 3 and 3, fact, and y will be between negative 5 and 5. And, okay, we did this in class already, so maybe this is already sort of very familiar to you, or should be, that if you consider sort of background knowledge previously discussed, not on this video, that x equals cosine, y equals sine parameterizes the unit circle. That if you pick a point on the unit circle, then you can actually think of, you should think of, the length of this arc taking you from 1, 0 to the point on the unit circle as having length t, then the very definition of sine and cosine is that if this is the unit circle, then this is cosine t comma sine t. That's just the definition of sine and cosine. So in other words, cosine is the x-coordinate and sine is the y-coordinate. Thus, this parameterizes the unit circle. And this is basically the same thing, except x is being stretched by a factor of negative 3, and y is being stretched out by a factor of 5. So I think you already have a pretty good guess what this is going to look like. It's going to look like a circle, except a circle which has been stretched out by 3 in the x direction, stretched out by 5 in the y direction, and yet somehow this negative is going to also do something in some kind of way. Okay, well, having done restrictions, of course I can take the sine and cosine of anything, so there are no restrictions on t. There's no end behavior to talk about. What else? The boundedness of x and y has already been built in here. What more is there to say? I thought there was going to be one more thing I was going to say, but I can't remember. Oh yeah, of course they each have period 2 pi, these two functions, so if x takes 2 pi to repeat and y takes 2 pi to repeat, the whole curve is going to be repeated every 2 pi. And so we just do it now. So, what are we going to do? Well, okay, I will just maybe graph this thing right now. And yeah, what I say, the x-coordinate is going to be stretched out by 3, cha-cha. The y-coordinate is going to be stretched out by 5. And you can actually sort of barely know what you're doing and get a pretty accurate graph here because just plugging in some points, right? When t equals 0, cosine 0 is 1. And so we end up at -3, comma 0. So actually I am here, that was maybe a little bit surprising, at -3, comma 0 at time t equals 0. Another good number to plug in would be pi over 2. Cosine pi over 2 is 0. Cosine pi over 2 is 0, but sine of pi over 2 is 1. So then I get to this point up here, 0, comma 5. And that is t equals pi over 2. And so, okay, so this must be going kind of like this. So, I mean, I think I pretty much just know that this is going to be like an oval. But if I plug in pi, cosine pi -1, but -3 times -1 is +3. So I end up out here at 3, comma 0 at t equals pi. And it must be that I'm here at t equals 3 pi over 2, 0, comma -5. If I plug in 0 for, sorry, if I plug in 3 pi over 2, cosine 3 pi over 2 is 0, sine 3 pi over 2 is negative, so then I get 0, comma -5. So the only thing kind of interesting here is that we start over here and we go kind of that way. Yeah, cha-cha. Cha-cha, 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 cha-cha. Okay, and maybe the final thing, notice how I didn't even bother really eliminating the parameter. But if you really want to, you can, because it's just true that cosine squared t plus sine squared t is 1. What is cosine squared? Well, it's x squared over 9. And what is sine squared? Well, it's y squared over 25. So, if you want to, you can write it like that, but that doesn't really help you unless you already know some things about graphing equations like this. So in some ways, maybe this is a nice introduction to equations like this. Okay, I'm going to pause this video for a second and be right back. Okay, we're back. Let's do this one. Okay, this is kind of a weird problem. I usually don't go over this one. Maybe it's not that exciting, I don't know. Here we go. Never seen this before, have no idea what to expect. So let's check it out. Well, first off, notice that t can't be 5, of course. Well, if t can't be 5, then of course y then also can't be 5, so let's put that there as well. And notice more things. That if t can't be 5, maybe that's all there is to say. T can't be 5. Well, okay, one thing to notice is that this fraction can never be 1 because the numerator is always going to be a little bit different than the denominator. So I also noticed that x can't be 1. Maybe there are other things to say about this. If you want it to be really, really awesome, what you might do right now is, you might do several things. You might make a tiny sign chart, okay, of x, and looking at different kind of t values, you can see that this is going to change sign at 3 and 5. So this is going to be plus, minus, plus. These are, maybe I'll put t down here just to indicate that this is the sign of x for different values of t. Well, that might be a useful thing to know. I got another useful thing that you might do. You might do polynomial long division. Or, if you're a little bit cooler, you could avoid polynomial long division by just doing something which I mentioned in a previous video that people do in these kind of situations, which is they just sort of subtract 2 and add 2. y, because then that numerator becomes t minus 5 plus 2. And then you split up the fraction. And so what we get is that x is 1 plus 2 over t minus 5. And maybe that explains a little bit more why x can never be 1. And kind of maybe demystifies a little bit that original expression. After all, it's just a rational expression, so doing polynomial long division when the degree of the numerator is greater than or equal to the degree of the denominator is kind of like a thing to do. Okay, so having done all this work, maybe I have time to just get started now. What do we need to do? We need to look at the end behavior, but we really also need to look at the values of t near 5. Alright, so the full solution here would involve us looking at what happens as t approaches infinity, what happens as t approaches negative infinity. I might not have enough space to fully carry this out, but also we should look at what happens as t approaches 5, and of course it's going to matter whether t approaches 5 from the right or t approaches 5 from the left. So let's just do this problem properly. Okay, well, you have two options, I guess. Do you prefer to use this form or do you prefer to use this form? To me, it's just much clearer to use this form. Of course, if I plug in a number that's really big, like 1,000,000, then 1 second. Then that is basically like 1,000,000 over 1,000,000, so you can see that that's 1, but it's going to be a little bit less than 1 because the numerator is always going to be a little bit smaller. So I think the end result here is 1 minus, but maybe it's even easier to see from this form, right? If you plug in like what happened? It's not 1 minus. What did I say? 1,000,000? Oh, being kind of dumb. If you plug in 1,000,000, that's interesting. If you plug it, I was being a little bit wrong there. If you plug in like 1,000,000, you're subtracting 3 from the numerator, but 5 from the denominator. So in fact, the numerator is bigger, and so you should expect this to be a little bit more than 1. Haha. It was much easier on my little brain to consider this formula, because now as t goes to infinity, you can see that that's 2 over huge is going to be a tiny positive. So 1 plus a tiny positive is 1 plus. So I think it is easier that way. Okay, here of course y will go to infinity because y just is t. How about as t approaches negative infinity? Okay, here, I mean, my mind is really just boggled now, right? Like a negative 1,000,003 over negative 1,000,005, that's too hard. I really like this representation. Now I can see at a glance that as t goes to negative infinity, that's going to be like 2 over huge negative. 2 over huge negative is a tiny negative, so I'm adding a tiny negative to 1, and that's why x is going to be a tiny bit, what did I say? I'm adding a tiny negative to 1, so x is going to be a tiny bit less than 1. And y is going to be negative infinity. That was pretty hard. Once again, yeah, this step is just indispensable, because now, if I'm a little bit more than 5, then I can just glance right at this and see, okay, a little bit more than 5, the denominator is a tiny positive. 2 over a tiny positive is a huge positive, so x is going to infinity, and y is just going to 5 plus, because once again, y just is t. If t goes to negative, if t goes to 5 minus, then if t is a tiny bit less than 5, a tiny bit less than 5 minus 5 is a tiny negative. 2 over a tiny negative is a huge negative. So that's 1 plus a huge negative, so x is going to negative infinity. And y is going to 5 minus. So actually that was kind of hard. I see now that this problem is a little bit trickier than I thought. I'm going to need 2 boards for this. Well, what's left to do now? Let's eliminate the parameter and then graph it. Okay, well, eliminating the parameter, how am I going to do that? Well, probably the simplest thing to do is to just stick in y for t. So you get x equals y minus 3 over y minus 5. And okay, I'm not going to repeat the whole speech from 10 minutes ago or 20 minutes ago or whatever, but yeah, this is kind of like, you know, this just doesn't do anything for me, because I don't know what this is. So, you know, I have a lot of experience graphing, but I don't have any experience graphing this, so that's just too hard. So I think the thing to do is solve for y. Embrace your y equals bias in this case. So multiply both sides by y minus 5, so you get x y minus 5 equals y minus 3, and then let's just solve for y now, right? So xy minus 5x equals y minus 3, subtract xy minus y equals 5x minus 3, factor out a y, that's x minus 1, and finally divide, and you get y equals 5x minus 3 over x minus 1. So this is actually quite a lot going on here, because though that is a pretty good way of writing this problem. Did I do all this? Look, I haven't looked at my answer key in years for this problem. I think I want to do polynomial long division. I mean, that's like the good student thing to do in this situation. It is a rational function after all. So dividing through by x minus 1 gives me 5x minus 5. And what do I get? This is 2. Negative 3 minus negative 5. So what is this really? This is y equals 5 plus 2 over x minus 1. Alright, and now this is completely under control. I know exactly how to graph y equals 5 plus 2 over x minus 1. It's just going to be what it is. This curve is going to be moved up 5. Cha 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 cha. 1 to the right. So boom 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 boom. And otherwise, it's going to be a 1 over x curve, but stretched out by a factor of 2. So notice x can't be 1, y can't be 5. And yeah, this whole thing is just going to be, I guess I'll have a point 2 comma, instead of 6, it will be 2 comma 7. And how do I do this again? Instead of 4, when I plug in, oh man, when I plug in 3, I get 6. I think I did that right. So yeah, so something that looks like that. That's 2 comma 7. I hope I'm not messing this up. When I plug in 2, yeah, 2 comma 7, 3 comma 6, and I'll have more sort of points like that over here. You plug in 0, and you get 3. And then I'll have this point here, I think. Negative 1 comma 4. Let's just double check that that's right. It just is. So something like that. And then we cross. Okay, so negative 1, 4, and 0 comma 3. Alright, there's my curve. How is this curve being traced out? I don't know. Let's start at time negative infinity. Where am I? I am at 1 minus comma negative infinity. So there I am. This is a little bit less than 1 comma negative infinity. This is t equals negative infinity. And now I must be going kind of up this curve. And what's the next kind of thing that's interesting? What happens as t approaches 5 minus? Well, if I'm at time a little bit less than 5, then I'm at negative infinity comma a little bit less than 5. So this right here is t equals 5 minus. And what happens at t equals 5 minus? Instant teleportation from time t equals 5 minus to time t equals 5 plus. And according to all my kind of hard work from the preparatory phase, I see that at time 5 plus, I'm at infinity comma a little bit more than 5. And so I had sort of my arrows going like this. Cha 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 cha. And finally, as t approaches infinity, I'm approaching a point which is a little bit more than 1 comma infinity. So this whole thing pretty much just makes total sense. If I wanted to be cool, I could plug in some more t equals values, say, I don't know, what's a good one? If I plug in 4, I think I get 1 comma 4. No, if I plug in 4, I get 1 over negative 1, so I get negative 1 comma 4. So this point here is t equals 4. And, oh, okay, I bet I can just do this, right? Because if I plug in t equals 3, then now that will be this one. So this is all making sense. And it's just going to keep making more sense. Because, look, if I plug in t equals 6, yeah, then I get 3 comma 6. So this is t equals 6. And this will be t equals 7, actually. So it's all making total sense. Okay, the problem is a little bit harder than I thought. All right, we need to save some more mental energy for the last problem on this packet, which I think is actually pretty hard. This is an exact repeat. Well, it's not an exact repeat, but it's essentially a repeat of a problem that we did on the first packet, number 8, which I thought was very, very hard. So I think this is also very, very hard, but you know, the second time you see something, it's a little bit easier. And I think I picked the numbers a little bit more nicely here so you get all integers, but some of them are negative, so okay, it is very tricky. You have to be very, very careful, and I think when you're done with this problem, if you take it really, really seriously, you're just a lot smarter. Okay, without further ado, this is going to take like 20 minutes. Hopefully, maybe not. Let's do this. What do I notice? I notice t can't be 2. And I also notice that t can't be 5. But also, I notice that since t can't be 2, that denominator will never be negative 3. So this will never be 6 over negative 3. So y will never be negative 2. Let's make sure I did that right. 6, yep, 6 over negative 3. Y will never be negative 2. Okay, more. Well, since t can't be 5, then that denominator will never be 3. And if that denominator will never be 3, then x will never be negative 1. Okay. And x and y will each never be 0. X can't be 0 and y can't be 0 because they're always, you know, the numerator is never 0. Okay, those are all the restrictions. Now the end behavior part, which I think is the hardest part. So I need to look at so many things. I need to look at what happens as t goes to infinity. What happens as t goes to negative infinity. But also, I think it's clear that near t equals 2, things go nuts. So I better examine what happens as t approaches 2. If t is both a little bit more than 2, and t is a little bit less than 2. Okay. And what about as t approaches 5, things go crazy. So I need to see what happens as t approaches 5 a little bit more, and as t approaches 5 a little bit less. Okay, so the full solution to this problem requires you to go through all this logic, which I think is really hard. Let's do it. Well, as t approaches infinity, you get negative 3 over a huge positive, so negative 3 over a huge positive is going to be a tiny negative. And y, 6 over a huge positive, is going to be a tiny positive. As t approaches negative infinity, now the denominator is like negative a million, but negative 3 over negative a million, the negatives cancel, and so x becomes a tiny positive again. Might want to watch this on 1 speed. What about now? T goes to negative infinity, that's 6 over like negative a million, so that's going to be a tiny negative. Okay, I think I did all that right. Now let's see what happens if t is a little bit more than 2. If t is a little bit more than 2, that's a tiny positive down there. But what is negative 3 divided by a tiny positive? That's going to be a huge negative number. Down here is where things get hard. 2 minus 5, what is that? Well, it's basically negative 3. So this is basically 6 over negative 3. So y is definitely going to negative 2. But I'd like to know whether it's a little bit more than negative 2 or a little bit less. For this I need to be very careful, and I need to say, okay, if t is a little bit more than 2, that's like 2.1. If that's 2.1 down there, then this is like negative 2.9. What is 6 over negative 2.9? Well, ignoring the negative for a minute, 6 over 2.9 is certainly bigger than 6 over 3. Because 6 over 2.9 is bigger than 6 over 3, the denominator got smaller, the fraction got bigger. Therefore, 6 over negative 2.9 is going to be a negative number whose magnitude is larger than 2. In other words, this is going to be negative 2 minus. That was very hard. Let's do it basically 3 more times. So okay, as t approaches 2 minus, now that's a tiny negative down there, because a little bit less than 2 minus 2 will give me a tiny negative. But negative 3 over a tiny negative, the negatives cancel and we're going to get a huge positive. How about y? Once again, if you plug in basically 2, that's basically negative 3 down there. 6 divided by basically negative 3 is basically negative 2. But is it a little bit more than negative 2 or a little bit less? Well, if t is a little bit less than 2, like 1.9, what is 1.9 minus 5? That's like 3.1. So that's a negative 3.1 down there. So once again, temporarily ignore the negative and just ask yourself, 6 over 3.1, is that more than 6 over 3 or less? 6 over 3.1 is going to be less than 6 over 3 because the denominator got bigger. So this is going to be a smaller than 2. The magnitude of y is going to be smaller than 2. In other words, this is negative 2 plus, because this is going to be a negative number which is smaller, so to speak, than negative 2 is. Okay, 2 more. As t approaches 5 plus, well, I have a similar kind of work to do now, right? 5 minus 2 is basically 3. So if that denominator is basically 3, negative 3 over 3 is basically negative 1. And is it going to be a little bit more than negative 1 or a little bit less? Well, if t is like 5.1, 5.1 minus 2 is like 3.1. Negative 3 over 3.1, well, ignoring the negative, 3 over 3.1 is going to be smaller than 1. This is going to be a smaller magnitude number than the magnitude of negative 1. So this is negative 1 plus. And for y, if you plug a tiny positive, if you plug a number a tiny bit more than 5, minus 5 is a tiny positive, 6 over a tiny positive is infinity. Okay, one left. If t is 5 minus, then once again, that's pretty much 3 down there. Now, negative 3 over 3 is pretty much negative 1. Is it a little bit more than negative 1 or a little bit less? Well, if that's a little bit less than 5, say 4.9 minus 2 is 2.9. What can I say about 3 over 2.9? 3 over 2.9 is a bigger in magnitude number than 1. So this is going to be a negative number whose magnitude is more than the magnitude of negative 1. In other words, negative 2 minus, a number to the left of negative 1. Man, that is so hard. And down here, if you give me a number which is a tiny bit less than 5, minus 5, that's a tiny negative. 6 over a tiny negative is a huge negative. Alright, this problem, like I was saying, is a giant smart pill. If you got all this right, you're just so good now at stuff. We're like ready for calculus. Alright, and if you do all that right now, the problem kind of just can't go wrong now if you do all that stuff right. Alright, what's left to do? Eliminate the parameter and graph it. Let's go. How do I eliminate the parameter? Well, I have the y equals bias. So I'm going to take x equals negative 3 over t minus 2. And I shall manipulate it as follows. Divide both sides by x, multiply both sides by t minus 2. So we get to t minus 2 equals negative 3 over x. Well, that means that t is in fact 2 minus 3 over x. Okay, now stick that in for y. So y is 6 over 2 minus 3 over x minus 5. And don't stop there, because this is just some garbage at the moment, so I need to do more things to make it more clear. What do I end up with? I end up with 6 over, that's negative 3 minus 3 over x. So actually, one thing we could do kind of right now is divide the top and bottom by negative 3. That seems like a good thing to do. So you get y equals negative 2 over over 1 plus 1 over x. Not sure that was necessarily the best thing to do, but the clearest thing to do, but it definitely works. I just divided the top by negative 3 and I divided both of those by negative 3. That seems a lot simpler to me. Okay, one more thing is I don't want like kind of fractions inside of fractions if I can get away with it. So think of that 1 as x over x. And so this is really like negative 2 over x plus 1 over x, which is really negative 2x over x plus 1. And alright, that's pretty good, but I want it to, well, that's a rational function, so I'm going to do polynomial long division. So negative 2x divided by x plus 1, squeezing this in here, goes in negative 2 times, and that's negative 2x minus 2. When you subtract that, you get 2. Alright, so there are 2 ways in which I could express this curve. Y equals negative 2x over x plus 1, which shows me that I have a root at 0. So that's nice. And I could even make a nice sign chart off of that. And then the other expression, arguably even more important, is that this is really just negative 2 plus 2 over x plus 1. That shows that this is really just like a 1 over x curve, but moved down 2, moved 1 to the left, stretched out by a factor of 2. Okay, so keeping kind of both of those in mind or something, I now can graph this. What's it going to look like? Move down 2, cha-cha-cha-cha-cha-cha. Move 1 to the left, so boom, 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 boom. And yeah, otherwise it's just a regular 1 over x type curve with a root at 0. So something that's going to look like that and like that seems good enough for me. Now I look back at my restrictions and I see, as predicted, x can't be negative 1, y can't be negative 2, but also neither x nor y can be 0. And when I start to examine in chronological order kind of what happened here, I see what's going on, right? Let's do this chronologically. At time negative infinity, I am here at 0 plus comma 0 minus. 0 plus comma 0 minus. In other words, down here at t equals negative infinity. Just to the right of and below the origin. And so I'm never equal to 0, 0, and it sort of takes me an infinite amount of time to get away from that hole there. And what's the next thing that happens? Well, at time 2 minus, I'm at infinity comma a little bit more than negative 2. So it's all happening kind of exactly as predicted. At time t equals 2 minus, I teleport instantaneously from that point to this point at t equals 2 plus. Because according to my calculations, at t equals 2 plus, I'm at negative infinity comma a little bit less than negative 2. And then I zoom down this way, and then another teleportation happens as t approaches 5 minus. I'm at negative 1 minus comma negative infinity. In other words, a little bit less than negative 1 comma negative infinity. So here, maybe let's do a pentagon, just for fun. So this is t equals 5 minus, and I teleport up to here at t equals 5 plus, which is negative 1 plus, in other words, a little bit more than negative 1, comma infinity. And then down, 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 And the final answer is that as t approaches infinity, I slowly approach the origin again, but I'm always a little bit, my x is always a little bit less than the origin, my y is always a little bit more. So this is t equals infinity. Cha-cha. Okay, that's pretty cool. So it starts off here, and then, and if you want to be kind of exciting now, you can plug in some more points. I don't know what's a good number to plug in. Maybe I just won't do that because I don't want to like risk it or something. I don't know. What if I plug in -1? Is that a good idea? At time -1, where am I? I think I'm at 1, comma, -1. So boom, here I am at 1, comma, -1 at t equals -1. Can I think of another good number to plug in? I'm not sure I can. Maybe t equals like 4? Yeah, that's a good one. If you plug in t equals 4, you get -3 halves. I guess that's not too bad. And -6. Sure. So -3 halves, -6. I wanted all integers, but anyway, that's t equals 4. Maybe if I plug in t equals, no, I don't know if there are too many other good numbers. I could have plugged in t equals 0, then I get 3. No, that's not nice either. Anyway, that seems good enough for me. All right, that took forever, but that's parametric part 2. Woo!